Good morning. So I'm going to go over the solutions to the problems on the midterm exam. And problem number one had to do with prime numbers. So just recall the definition. It's actually part of the problem. A prime number, make sure I can put this all on the screen. A prime number is an integer, let's say n, greater than 1, that means greater than or equal to 2, whose only positive integer divisors, are 1 and n. So a prime number is a positive integer that has exactly 2 positive divisors. And if you take the last 3 digits of your social security number, for example, if you take, in my case, 618, every number is a product of primes. If you factor this, let's see, we do it in steps. Like I can say this is divisible by 6. This is 6 times 103, and 6 is 2 times 3, and 103 is a prime, 2 is a prime, 3 is a prime. So this is a factorization of 618 into prime numbers, into primes. And we want to prove Euclid's theorem, which says that there are infinitely many prime numbers. And the proof goes as follows. Let P1, P2, P3, up to P sub k be any finite set of primes. We define an integer, let me write capital N, which is the number you get when you multiply all of these primes together, P1, P2, P3, up to P sub k, and you add 1. So dividing n by any of the primes P sub I, P1 up to Pk, leaves a remainder of 1. So n is not divisible by any of the primes P1 up to P sub k. But every integer greater than or equal to 2 is either a prime or a product of primes, is divisible by some prime, q. So there exists a prime q different from P sub I for all I going from 1 up to n, or 1 up to k, for all of these k primes. So there's no finite set of primes. So the number, so the set of primes must be infinite. There are infinitely many primes. And that's the proof. Problem 2 is to find the quotient and remainder when one integer is divided by a number. So recall the division algorithm. If you have any numbers a and b, so given integers a and b, with b at least 1, there exist unique integers, q and r, such that a equals bq plus r, and this remainder r is at most b minus 1 and greater than or equal to 0. So suppose I take a equal to 425 and b equal to 52. So 425 is in fact 52 times 8. Let's see, what is 52 times 8? It's 416 plus 9. So here I've written 425 as a multiple of 52 plus a remainder. So Q is, my quotient is 8. And in this case, my remainder is 9. Suppose I take A equal to minus 425 and B equal to 52. I mean, I could multiply this equation by minus 1. I would get minus 425 is 52 times minus 8 minus 9. But minus 9 is not the remainder when you divide by 52, because minus 9 is negative. The remainder has to be 0. But I could say the following: if I add 52 to this, I get, I could say this is, or let me subtract and add. Let me do this in 2 steps. So this is 52 times minus 8 minus 9. And let me say minus 52 plus 52. I've just added 0. And this is 52 times minus 9 of them, I guess. And 52 minus 9 is 43. So minus 425 is 52 times minus 9 plus 43. And so in this case, the quotient is minus 9, and the remainder is 43. Remember, remainder in the division algorithm is never negative. So that's the answer. In part B, we have a similar problem involving congruence classes. So if you have any number a and any integer n, you can always find an r such that a is congruent to r mod n, with this r between 0 and n minus 1. This is the least non-negative residue of a modulo r. So for example, if we take a equal to 73 and the modulus n to be 19, you know, if you divide 73 by 19, 73 is, let's see, it's actually 3 times 19, 19 times 3, that's 57 plus 16. So this means that 73 is congruent to 16 modulo 19. So this is the least non-negative residue. If you look at minus 73, if you let a equal minus 73 and n equal 19, you could say, if you multiply this by minus 1, minus 73 is 19 times minus 3 minus 16. So it's true that 73 is congruent to minus 16 mod 19, but minus 16 is positive. It's not a least non-negative residue. So that's a true statement, but it's not the answer to this question. What you would say is that, I mean, you could say this is 19 times minus 3 minus 19 plus 19 minus 16. And if you look at this, this is 19 times minus 4, and 19 minus 16 is 3. So one gets minus 73 is congruent to 3 modulo 19. So the least non-negative residue of minus 73 mod 19 is 16. And if you just wanted to check, minus 73 minus 3 has to be divisible by 19, but this is minus 76. And this is, in fact, 19 times negative 4. So this does check. And that is the solution to problem 2. In problem 3, we want to use the Euclidean algorithm to find the greatest common divisor of 567 and 245. So the Euclidean algorithm is a process of successive division. 567 is 245 times 2. Let's see, that's 490, and that leaves a remainder of 77. If you take 245 and divide by 77, let's see, 3 times 7, 77, is 242. No. Let me just do my calculation. 3 times 77 is 231. So this is 77 times 3, and 245 minus 231 is 14. And if you take 77 and divide it by 14, that goes in 5 times and leaves a remainder of 7. And if you take 14 and divide it by 7, you get a quotient of 2 and a remainder of 0. So the least non-negative residue of, the greatest common divisor, the GCD of 245 and 567 is 7. So that's part A. And for part B, we want to write 7 as an integral linear combination of 567 and 245. So you just go backwards through the Euclidean algorithm, trying to do the arithmetic carefully. This says that 77 is equal to 77 minus 14 times 5. The second equation says this is 77, let me write this as minus 5 times 14, but 14 is 245 minus 77 times 3. So if you collect that, I have 77 plus 5 times 3, 15. I have 77 times 16 plus 245 times minus 5. And from my first equation, 77 is 567 minus 245 times 2. So all that times 16 plus 245 times minus 5. So this is 567 times 16. And how many 245s? I have minus 32 minus 5, so that's plus 245 times minus 37. So this is 7 written as a linear combination of 567 and 245. So, or another way to state that in the form of the problem, 7 is equal to 245x plus 567y with x equal to minus 37 and y equal to 16. In problem 4, we're told that A1 is congruent to A2 modulo n, which means A1 is A2 plus some multiple, called R times n. And we're told that B1 is congruent to B2 mod n, which means B1 is equal to B2 plus some other multiple, say S times n. So if you multiply A1 times B1, that's the same as A2 plus Rn times B2 plus Sn. If you multiply that out, you get A2B2 plus A2Sn plus RnB2 plus RSn squared. This is equal to A2B2. And from this, I can factor out an n times A2S plus RB2 plus RSN. In any case, A1B1 is A2B2 plus a multiple of n. So that means that A1B1 is congruent to A2B2 mod n, which is exactly what we had to prove. Okay. Problem 5 is to solve some linear congruences. We want to find all solutions of 5x congruent to 13 mod 7. So there are many, many different ways to do this. We can observe, for example, that 13 is congruent to 6 mod 7. Or that 13 is congruent to minus 1 mod 7. So we could rewrite this congruence in either form. For example, 5x congruent to 6 mod 7. That means we want to find all integers x such that 5 times x minus 6 is divisible by 7. I mean, there are lots of ways to do it. You could make a little table. Here you write x and 5x, but I want to write 5x mod 7. Let's make it like this. So if x is 0, 5x is 0, and 0 is 0 mod 7. If x is 1, 5x is 5, and 5 is congruent to 5 mod 7. If x is 2, 5x is 10, and 10 is congruent to 3 mod 7. If x is 3, 5x is 15, 15 is congruent to 1 mod 7. If x is 4, 5x is 20, 20 is congruent to 6 mod 7. That's what I wanted. I can stop right there, we win. So one solution is x equal to 4, right? 20 minus 6 is 14. Or if we looked at this, 20 minus 13 is 7. They're both divisible by 7. So 4 is the solution. And in fact, all solutions are all x congruent to 4 mod 7. In fact, if you also just wanted to look at all other possible congruence classes, if you took x equal 5, this would be 25, and mod 7, that's 4. If you did x equals 6, 5x is 30, and mod 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, that such that 5x is congruent to 6 mod 7 for x between 0 and 6. And anything congruent to x to 4 mod 7 will also be a solution. So that's the set of all solutions. Problem number 6. Sorry, not problem number 6. The second part of this, this is A and this is B. This is to solve two congruences simultaneously. We want to find all x such that x is congruent to 9. Sorry, x is congruent to 2 mod 9. And also x is congruent to 3 mod 7. So if you know the Chinese remainder theorem, 9 and 7 are relatively prime, so you know this pair of congruences has a solution, but we have to find the solution. So we can say the following: if x is congruent to 2 mod 9, then x has to be a number of the form that say 2 plus 9 times y. And this number also has to be congruent to 3 mod 7. So we have to find y such that 2 plus 9y is congruent to 3 mod 7. That's the same as saying 9y is congruent to 3 minus 2, or congruent to 1 mod 7. And 9 is the same as 2 mod 7. 2y is congruent to 9y, congruent to 1 mod 7. So we need to find y such that 2 times y minus 1 is divisible by 7. And you can just check, like 2 times 4 is 8. 8 minus 1 is 7. So y can be any number congruent to 4 mod 7. That is, y is any number of the form 4 plus 7 times z. And the number we're looking for, x, is a number 2 plus 9 times y. So that's 2 plus 9, and y is 4 plus 7z. So this is 2 plus 36 plus 63z, or 38 plus 63z. So any number of this form is a simultaneous solution of those two congruences. And the set of all solutions, all x congruent to 38 modulo 63. And again, you can check. What is 38 minus 2? It's 36 is divisible by 9. 38 minus 3 is 35 is divisible by 7. So that's a check that this is correct. In problem 6, we have a permutation, sigma. It's a permutation of the numbers from 1 to 7. And in this permutation, it's given in standard form by 5, 4, 6, 7, 3, 1, 2. And if we want to write this as a product of disjoint cycles, we can just follow numbers through the cycle. 1 goes to 5, 5 goes to 3, 3 goes to 6, 6 goes back to 1. Let's see, we haven't looked at 2 yet. 2's not here. What about 2? 2 goes to 4, 4 goes to 7, 7 goes back to 2. So these are disjoint cycles. And we can write this as a product of transpositions in many different ways. One simple way, if you remember the algorithm, is 1, 5, 3, 6 is the same as 1, 5, 5, 3, 3, 6, and 2, 4, 7 is the product of two transpositions, 2, 4, and 4, 7. So these are not disjoint, but these are transpositions. What is sigma squared? Sigma squared is the permutation that you get by applying sigma and then applying it again. It's the composite function, sigma composed with sigma. So in sigma, 1 goes to 5 and 5 goes to 3. 2 goes to 4, 4 goes to 7. 3 goes to 6, 6 goes to 1. 4 goes to 7, 7 goes to 2. 5 goes to 3, 3 goes to 6. 6 goes to 1, 1 goes to 5. 7 goes to 2, 2 goes to 4. So that's sigma squared. And as a product of disjoint cycles, 1 goes to 3, goes back to 1. 2 goes to 7, goes to 4, goes back to 2. See, 5 goes to 6, goes back to 5. So this is also the decomposition of sigma squared as a product of disjoint cycles. And sigma inverse, that's the permutation that is the inverse function. It reverses what sigma does. So if sigma sends 6 to 1, then the inverse sends 1 back to 6. If sigma sends 7 to 2, the inverse sends 2 to 7. Sigma sends 5 to 3, so the inverse sends 3 to 5. Sigma sends 2 to 4, so the inverse sends 4 to 2. Sigma sends 1 to 5, so the inverse sends 5 to 1. Sigma sends 3 to 6, so the inverse sends 6 to 3. And sigma sends 4 to 7, so the inverse sends 7 to 4. So this is sigma inverse. And as a product of disjoint cycles, 1 goes to 6, 6 goes to 3, 3 goes to 5, goes back to 1. 2 goes to 7, goes to 4, goes back to 2. So that is the decomposition of sigma inverse as a product of disjoint cycles. Problem 7, a polynomial f of x is irreducible if the degree of f is at least 1, and f cannot be factored, is not a product of polynomials all of degree greater than or equal to 1. So for example, if we take the polynomial f of x equals x to the 6th minus 1, this is not irreducible. It factors. You can factor it in many different ways, but if you want to factor it completely, that's going to be unique up to the order of the factors. So you could think of this, for example, as x to the 6th is x cubed squared minus 1. And a square minus 1 factors into x cubed minus 1 times x cubed plus 1. But x cubed minus 1 factors into x minus 1 times x squared plus x plus 1. And x cubed plus 1 factors into x plus 1, x squared minus x plus 1. And these are degree 1, so they certainly don't factor. These are degree 2, but they also don't factor. That's as far as you can go. So this is the decomposition or the factorization of f of x into irreducible polynomials. So this polynomial is a product of these 4 irreducible polynomials. They're irreducible over the rationals. Problem number 8 is just to do the Euclidean algorithm long division for polynomials. So we have 2 polynomials, f of x equals x to the 4th plus x cubed. plus 2x squared plus x plus 1. And g of x equal to x cubed plus x squared plus x plus 1. And the division algorithm for polynomials says that for any polynomials f of x and g of x, you can write f of x as g of x times some quotient polynomial called q of x, plus a remainder of r of x, where either r of x is the zero polynomial, or the degree of r is strictly less than the degree of g. So this is completely analogous to the division algorithm for integers. So let me apply the division algorithm or calculate the quotient and the remainder. Here's the quotient, here's the remainder. So let's do it the old-fashioned way, if you like. X cubed plus x squared plus x plus 1, dividing that into x to the fourth plus x cubed plus 2x squared plus x plus 1. So if you look at x cubed into x fourth, that goes x times. Plus x times this is x to the fourth plus x cubed plus x squared plus x. And you subtract, you get x squared plus 1. And this doesn't go into this. So we have f of x. I'll write this in two ways first. F of x, that's this polynomial, is equal to g of x times x plus the remainder of x squared plus 1. So this is the quotient polynomial, and this is the remainder. So the quotient, when you divide f of x by g of x, is x, and the remainder is x squared plus 1, and the degree of x squared plus 1 is 2, which is less than the degree of what you're dividing by, x cubed plus x squared plus x plus 1, which is 3. So this polynomial has lower degree than what you're dividing by. And then if you want to write this greatest common divisor as a combination of f and g, well, we almost have it right here. So x squared plus 1 is equal to f of x minus g of x times x. So here I've written the GCD of the polynomials f and g. It's the polynomial f times 1 plus the polynomial g times minus x. That's the expression. Oh, I'm sorry. This is true, but this is not what I was being asked to do. So this is correct. Part A is to use the polynomial division algorithm to compute the quotient of f when you divide by g, the quotient and the remainder, and that's what this is. So the quotient is x, and the remainder is x squared plus 1. But if I want to find, use the Euclidean algorithm, let me just do it right here. So this requires one or two more steps. So x to the fourth plus x cubed plus 2x squared plus x plus 1, that's my f, is equal to g, x cubed plus x squared plus x plus 1. times x and a remainder of x squared plus 1. Then I take x cubed plus x squared plus x plus 1, and I divide it by x squared plus 1. This is x squared plus 1, and x squared plus 1. If you divide x squared plus 1 into x cubed plus x squared plus x1, you actually get, well, let me do it. So everything is clear. X squared plus 1 into x cubed plus x squared plus x plus 1. So this goes in x times. I get x cubed plus x. When I subtract, I get x squared plus 1. When I divide x squared plus 1 into this, that goes in one time, and it leaves a remainder of 0. So this is x squared plus 1 times x plus 1. And so the last non-zero remainder is x squared plus 1. So the GCD is equal to x squared plus 1. That's the Euclidean algorithm. Problem 9, the last problem, is to define the root of a polynomial and prove something about it. So the number a is a root of a polynomial f of x if f evaluated at a is 0. So suppose, that if you divide the polynomial f of x by x minus a, you get f of x is x minus a times some quotient plus a remainder, where either r of x is 0 or the degree of r of x is less than the degree of what you're dividing by, is less than the degree of x minus a, which is 1. And the only integer which is greater than or equal to 0 and less than 1 is 0. So either r is 0 or the degree of r of x is 0, so that means r of x is a constant. Suppose a is a root. That means f of a is 0. If you plug in x equal to a, you get f of a is a minus a times q of a plus r of a. That's 0. But a minus a is 0. So this is 0 plus r of a equals 0. So r of a, this constant, is 0. So if a is a root of f of x, then when you divide f of x by x minus a, there's a quotient and the remainder is 0. So x minus a divides f of x if a is a root of x. If a is a root of f of x. And there it is, everyone. That's the whole exam. So we are done for today. Hello?
Oh,
Yeah, hi. I'm done taping the exam.
okay, all right. I'm sitting in the lobby with Alex, so.
Oh,
I'll be
okay.
back.
Well, that's fine. I still have more to do, but I'm done the taping, so I don't
Okay.
need quiet.
That's
So
good.
anytime is fine. All right.
Yeah.
All right. Bye.